First, questions about the project? Yeah, the project was Wednesday. Somebody emailed me, thank you. I had updated the document with the due date on Wednesday, but not the submission. I'm watching something sad.
I just wanted to make sure I understood the axis system. So our robot is sitting a meter above our global axis, let's say, and then the blocks are trying to hit the meter over the positions.
Yeah.
So we're fitting down into it. So
Yeah, so the pedestal goes up like this. I use X1, Y, right? X and Y. How do you do that in the most? Yeah. Okay. And this is like a meter column, right? The block sits out here. Here. Over. And 1 meter tall. Like that.
okay. And then theta 2, is that measuring between the first arm and the second arm?
Yeah, so exactly how it would be if you had a motor on there that drove this arm up to that angle and drove this to there down to that angle. Okay.
So theta 1 is off the y-axis. Theta 1 is off the y-axis. Okay. Okay. Right.
That should be in the lecture and the notes that we did when we did this a couple weeks ago. It should be posted. If you didn't go back and look at that, it should be on YouTube. All right, anything else?
Is there really any way to gauge like how good our numbers are? Because it says it's our number of training sets, the number of hidden neurons, and the testing RMS. How can we gauge if the numbers we're getting are actually good numbers, other than just they're better than the numbers we got before?
Well, I mean, you take your results file and you plot it so you can tell whether you're getting a good circle or a good X.
Yeah, but particularly with the number of hidden neurons and the number of training pairs.
Yeah, I'm not going to give you a target. I'm saying get the best you can. Within, I mean, I'm not giving you a year to do this. Right? I don't think you guys want to work on this for a year. Right? So yeah, I'm not going to expect anything else. But I mean, if you look at it, you'll be able to tell whether you're getting good results. I think 10% error is not real great. 1% error is really good, right? 0.1% error would be awesome. Anything else? Ask away. It's just, you on Wednesday, it's like your last chance. Short of coming to find me here, that's the class here.
To make sure I'm doing it right too. So you gave us the equations. So we develop our training pairs by picking our betas to get our XYs, and then we flip those to use other training pairs. Okay, and we just do as many as we want. Or
Yeah.
is there a recommended number and we just play around?
I would said the grade would depend upon how many hidden neurons, how many training pairs you use.
Oh, okay.
And I mean, you guys, you know you're going to have to post-process the results, right? Because you get the data out from the controller and then you have to run them back through the equations in Excel or MATLAB to generate your plots. But that's easy, all right? You just read in the file and you calculate. Okay, what else? We're going to start chapter 4 in the book today. We did some stuff in the book, and we did a bunch of applications, so we're back to the textbook. This is a chapter on competitive. And to introduce the idea of competition, the background doesn't really compete, right? It just takes the data in and runs its algorithm. So the idea here is that go back to the old iris problem. When we're looking at the iris, we want to classify into one of 3 categories. So we have this network that takes 4 measurements. And then we get the 3 categories as outputs. Cross connections here. Let's say we put in one set of data. How do those numbers here? All right, so let's say we put in those numbers for the measurements after we train the network. So this is after training. And we get out 0.7, 0.8, and 0.2. Is it Setosa, Virginica, or Versicone? What do you say? This one here, because it's slightly bigger than this. But then that's saying, hey, I almost think it's this one, right? So it kind of double classifies. It says the probability of it being this one's pretty low. Both of these are pretty much the same. So this is going to double classify. And what you did was you put in another layer above that where you introduced kind of a competition, right? You said, okay, I'm going to look at that, and 0.8 is bigger than 0.7, so I'm going to make it winner take all. And that one wins. Kind of like the outcome of an NCAA tournament game, right? One team wins, one team loses, one goes on, one stops. So instead of double classifying, we can say make competition between the outputs. In the extreme case, is winner take all. So that's the motivation for introducing competition in like this kind of classification problem. The networks that we're going to look at, I'm going to give you a real brief kind of overview introduction, and then we'll hit each one in more detail as we go along. So one of the things we're going to look at is something called a max. Another one is called Mexican crowd. And this one is a competitive network. Introduce the idea of how different neurons are competing against each other. And then the MaxNet is a recurrent competitive. Yeah, so I guess I listed these backwards. We're actually going to do this one first. This one second. So we're going to introduce the idea of competition and most people how competition works. And then the MaxNet is a recurrent competitive network. So you can see how recurrent connections along with appropriate weights can do calculations. There's no training in either one of these. So we'll do those. And then we're going to add in learning. Competition plus learning. And the learning is going to be what's called unsupervised. Meaning there's no teacher, there's no correct answers, but there's still learning that goes on. We talked about this last time on the back prop was supervised. I know it's a feed-forward network, we talked about feed-forward versus concurrent. Back prop is called supervised. Learning because there are target outputs. Whereas this, there will be no correct answers and no target. And the network figures out what goes where all by itself, just by looking at the data. The stuff under the categories under this are something called a self-organizing map. And I'll show you how we can take the iris data, the data set we used over here, and feed it into this self-organizing map, and it will cluster the 3 different categories of species all by itself. It's kind of cool, actually, how it works. It's a clustering algorithm. And then there's something called LVQ. Quantization. And it's kind of a supervised version of the component self-organizing map.
Could you put the screens down?
Yeah. Gladly.
Thank you.
Usually there's somebody up here sitting closer, and their job is not only to tell me to do that, but to catch the monitor if it starts to fall off. Are you ready for that? Hopefully it won't do that. And then there's another version that we'll get to called counter propagation. So again, we're looking at these different kind of networks, the competitive networks. And they can be used in control architectures, but we're kind of digressing now back to learning the basics of neural nets and these specific types of networks, what they do. So a broad overview of this powerful method of component self-organizing map. I want to give you an intro to that, and then we're going to go back to those other two, and then we'll come back to the details of this one. So it's unsupervised learning. I've already said that. This thing clusters data into groups. And we're going to introduce some new terminology. So I'm going to draw what are going to look like neurons. Because this was developed alongside neural nets, and so the people that developed it wanted to put it into the context of weights and inputs and activation. But what happens here is for neuron 1, there's a vector that are the weights. So there's a component of value for each one of these lines going in that look like inputs. So it's kind of like W11, W12, 1, 3, 1, 4, but it doesn't connect neurons into this one. Just, there's a vector associated with that. And then there's another vector associated with this, and another vector associated with this. And sometimes these are called weights for each of those units. So, new terminology. The first set is what you see there are output units. I'm not going to call them neurons, but you think of them as neurons. So they're output units. And in the new terminology, we call these clusters. And I deliberately chose 3 of them because you can think of this in terms of the iris problem, where this is the Setosa cluster, the Virginica, cluster, and the versicolor. And these E's are called several different things. You can say that they are weight vectors because they look like that, but they don't operate in the same way that there's a signal coming in, it gets multiplied by the weight, and then they're added in. That's not going on. More likely, we're going to call these exemplars. Because what's stored for this cluster that's called Setosa is a vector that represents that species. It's an example, kind of an average example of that species. And I'll show you why that's the case. And then over here, E2 is an average example of what Virginica looks like. And this is an average example of what versicolor looks like. So they're exemplar patterns. So that means, I guess it's Latin for example pattern. Sometimes they're called representative. Patterns because they represent that class of data. And occasionally you'll see these called codebook vectors. So here's how this thing works. Now again, we're going to go back to the iris problem. So let's say we have an input vector for the iris. We'll go back to that input vector, and I don't remember what numbers I used. Somebody tell me. What was the first input that I? What?
0.1,
Okay.
0.3,
Got it.
0.8,
0.15.
So there are 4 input numbers. And what it's going to do is compare I to each exemplar. And we need to talk about what compare means, but we're going to look at I here, and we're going to look at the E1 vector, and we're going to see how close I is to E1, or how close E1 is to I. And that's what we need to talk about, is how do you decide whether it's closer. One of them is the vector distance, which we'll use. And then it's going to compare I and see how close it is to E2. And the same thing for E3. And then it's going to pick the closest one, and then it's going to update the exemplar. Let's say it's this one here. It's going to update this exemplar here to be slightly more like the input. And then we're going to go back and grab another data set, another data point in the iris data set, compare it to each one, and then maybe 3 is a good match for that. And then we move this exemplar slightly closer to that input data set. So what's happening is, as this process goes on, each cluster starts grabbing onto data that it likes because it's closest to it, and then it moves itself closer to that input data. And that's how it learns. So we'll get into the details of the algorithm, but that's the basics. So I need to write that somewhere. So let's say I already said compare I to each exemplar, find the closest. I should be in my closet. Okay. Find the closest, and then update or move that exemplar, whatever it is. Let's say the closest is E sub k. Move E sub k slightly closer. Change the input. So I don't know, socially, I guess this is kind of like you come into a room with a whole bunch of people. Maybe, you know, you're going to college as a freshman, you want to live in the dorms, and you look and you find people that maybe come from the same area of the world that you do, or do the same things that you do, right? And you find out, well, you have things in common with them. And in the process, you start hanging out with them, and sometimes you take on their characteristics, right, of this group of people, and you become more like them. It's kind of like that. All right, so we have to define this. I think you can see how if you keep feeding this thing the data, no correct answers of what category, you keep feeding it, the ones that tend to be all classified over here, this thing moves more closer to being the center of that group of data. And so this starts grabbing onto hopefully all of the ones that are Setosa, and this one Virginica, and this one versicolor. And it really works slick. And again, you don't even need to know what the data represents. You can just run this thing and it'll say, hey, I'm noticing that this stuff looks the same, and this stuff looks the same, and this stuff looks the same. Now let's define closest, because we're going to need that. Not today, but a different time. Well, this is really, we're defining a metric. How do you measure distance? So the first one is the Euclidean. I guess it's called that because it uses Euclidean geometry. So if E is the exemplar, and the input vector is, well, it's the input vector. And this Euclidean distance called D subscript D is the exemplar to the input. is simply the square root of the sum of the squared distances. So this is the vector distance. This is how you calculate the distance between two vectors, and we're going to do a real simple example so you know where I did that. All right, so here's our real simple example. 2 dimensions. E is 1 comma 2. X is 3 comma 1. Gosh, I did it super easy. Right? Let's plot this. Here's 1. So what do we got? I want to plot B, so that's 1 over and 2x. That's E. And X is, no, sorry, I. This is the I is 2 over and 1 over. So this thing takes the difference between 1 minus 2 and squares it. So that's this distance, right? And then it takes this distance and squares it. And what do you get? Add those up. Sum of the two sides of the triangle squared. Add it up, take the square root, you get that distance. So the vector distance between those two. That's what that is. So let's calculate that. I'll give you a minute. Go ahead and do this. Plug these numbers into this formula and tell me how far apart vector-wise they are. Square root of 2, because you get 1 minus 2 is 1 squared is 1 plus 1 minus 2 minus 1 is 1 squared 1, so you get square root of 2. There's 2, something like that, right? How nerdy are you? How far do you know that out? How far do you know pi? 3? No, seriously, I mean, usually you end up sometimes punching in your calculator because you have a pi button, right? So you use 3.114.1592. That's about as far as I know. I think it's like 2, 5, something. I don't know. Somebody asked me that the other day that's not an engineer, and I didn't want to sound too nerdy, so I just went out.
I was actually using a scientific calculator on Google the other day, and they have like a game. There's like something that was shining. It was like 5. I clicked on it, and as you play like the memory game 5, or you touch it, the calculator, it tells you if you got it right. And then it just adds a new number each time.
So what you did? Just
I think I made it to like 20 something, but
wow.
like it basically repeats every time. So like it kind of trains you.
Oh, so you learn it and then you learn the next number and then it goes back and you get to do that.
You have to enter it in every time.
You know why I'm talking about this because it was like what last week was Pi Day. It was March 15th. The only reason I remember this because we went to Oak and Pie. You know, I already talked about this. The pizza restaurant out by Getty's near Target, and they had pizzas for $3 because it was Pi Day. It was a good deal. Okay, let's do another metric. There's another one called, what did I call that one? A. Called B. It's called the city block metric. You guys seen this one before? So let's draw our points again. I want to make it bigger. One, maybe two. We'll go through here. That's down here. The idea here is that you're in the city. There's buildings. And this is a serious city, so it's like that. There's buildings everywhere and streets in between. And who knows, maybe this is the Empire State Building. So if you want to go from this point here over to here, distance-wise, you can't go through the building, right? Maybe you can, but probably not. So you have to go. So that's what they call the city block metric. It's defined by some of the absolute values of each of the components. Because that's what you do. You just the x difference and the y difference, and you add up those absolute value. So now you know something else to impress your friends and neighbors. So what's the city block metric for our example? Think about it, even just lightly, not only like 10% of your brain power. You can probably figure it out, right? What's the distance up and down? Just looking at the picture. You go one down and one over, right? So this is kind of introducing you to the fact that there are different ways to measure distances between different objects in math and things like that. And if you really get into that and the mathematics of it, you take classes in topology and functional analysis, and you'll learn, well, how do you take distances between functions? Like how do you find the difference between the distance of sine of x and cosine of x? Stuff like that. Okay. So I've just added that in just for information. Typically we use this Euclidean distance when we calculate the distance for the suborganizer. But what we're doing when we do this, let's go back now. I just had one exemplar, one input, but let's say we go back to that iris problem, and there are 3 exemplars in that cluster. In other words, 3 clusters. What happens with the self-organizing map is that we put an input in. So here's our input. And we're finding which one of those is closer. We'll do this in local realism. So each one of these has kind of its region that it represents. And when you get within its region, it grabs onto that input data and says, it's mine, and I'm going to move a little closer to it. So the input shows up here, and then the weight training then moves the exemplar a little bit closer. And that formula looks exactly like a neural net weight update rule, because that's what it is that E mu is equal to E whole, and then this is E here is the closest. We pick the closest one, like E1, we'll always do it for E1. Because that's what we're doing in the picture here. No, it's like a weighted rule, doesn't it? So you can see why people go, oh, these look like neural nets. It says, pick the old weight exemplar, now we're not calling it weights anymore. And then we update it based on, well, it looks like that's the distance between the one you grabbed it and where it was. It's kind of an error. And the alpha is the learning rate. Which now is more maybe appropriate to call it the adaptation rate. And to better understand what this really does is to rearrange it a little bit. Let's collect the two E's together. I just moved this over here and factored out E old. And even better, let's put in a number for alpha. Let's make alpha 0.2. So what that says is the new exemplar is 20% of the input replacing 20% of the old exemplar. So we keep 80% of the old one and then we'll replace the other 20% with the input. And that is what moves it closer to the input. And so you keep doing that and you keep putting inputs in and each of these clusters move around trying to grab as many as they can. So there's the competition. And when it's all said and done, hopefully you have clusters that represent different unique groups of information in the network. All right, so I want to do the Mexican hat network and then we'll call it good for today. And really this is, I'm going to just show you the topology, how it's connected together. And we'll do it. And you'll see how the competition happens because there are connections, weighted connections in this that are excitatory and some are inhibitory. So we have to kind of jump our thought process away from these self-organizing maps back to neurons that behave more like what we talked about, where there are inputs coming in and they're weighted and we add them up and we apply an activation function. So to introduce these kind of competitive networks, we kind of got the preliminary definitions out of the way here, so we're going to go back to weighted connection networks. Here's the Mexican hat. And it's going to be looking like a toy problem, but this is actually a contrast enhancing network. You guys know contrast, right? Because y'all take photos with your phone and then you fiddle with them. And the contrast is the difference between the light and the dark regions of your photo. So you can either amplify the difference and make the dark regions darker and the light regions lighter, or decrease the contrast and make it more gray all over. So this network enhances contrast. What it does is it amplifies high values, it attenuates low values, and there's the competition. So it's an intro to competition via excitatory versus inhibitory. Psychologically, you can identify with that, right? We talk about how people have things that excite us, and yet we also have built-in inhibitions, right? We've, in fact, genetically built into us is, and learned behavior is the inhibition to running and jumping off a 20-foot cliff. Partially genetic, I think, pre-wired. Probably partially learned from when you were really small and you fell off of small things and it hurt. So we have an input vector coming in. Let's see, it said 1, 2, 3, 4, 5, 6, 7. 7. And then that matches the number of neurons. So we have 7. Seven neurons. So you have an input value for each neuron or a neuron for each input value. And what you do is you initialize the network values to the input. So you start the thing out. Remember on the recurrent nets we said we had to start out with initial values for the outputs of the neurons? Well, the values of these neurons are initialized to the inputs. And so I'm going to draw these 8 neurons. And we're going to process, or this is I'm going to teach you this by example rather than giving you all the theory. So here's our input signal. So then that becomes the value of all 8 neurons to start out. And then it processes through connections. And so we're going to focus on this neuron. These are going into number 4. So 4 takes its value, multiplies it by 0.6, and feeds it back into itself. So let's see, neuron 4 would be a 1. So we take 1 times 0.6, and that's going to be part of the net input for that neuron. And then 5 is going to multiply its value by 0.6. And that's going to go into the net input of 4. And so is 3. And this group is called nearest neighbors to the neuron that we're looking at the connection. So we're just looking at 4 and what's coming into it. Okay? And then neuron 2 is going to take its value and send it into 4. But it's going to multiply by negative 0.4. And 6 is going to send its value over to 4. And it's going to multiply by negative 0.4. So, looking at this, which connections do you say are excitatory? What?
The nearest neighbors.
Yeah. The 0.6s, right? Because it's going to take the values and multiply, and it's going to go into the inputs and make it more positive. And obviously, the negative ones are inhibitory. Because if this neuron's big, Like it has a big value here, it's gonna multiply by 0.4, negative and add into there, and it's gonna dominate and knock out some of the other inputs from the other neurons. This pattern is used for each neuron. So if we looked at 5 instead of 4, we'd see 6 feeding into 5, 5 feeding into itself, 4 feeding into 5 with 0.6. And then we'd see 7 and 3 feeding into 5 with the negative 0.4. You just shift that pattern centered on each neuron. And guess what these are called? With the inhibitory weights. What would you call them?
Our neighbors.
Foreigners? What is it? You
That's
guys
the
are
forest neighbors.
your forest neighbors, they're actually called not so near.
Oh,
Or you could call them farther away neighbors, right? So these are the guys that are on your cul-de-sac, and these are the guys that live in the neighborhood that are farther away.
same HOA.
I don't know, what are these neurons even further out that aren't even connected? Maybe their neighbors so far away you don't even know who they are. And if their dog gets in your yard, you don't know where the dog came from because you don't know the neighbors, right? All right, so then the other thing I need to tell you is, well, how does each neuron process? So we're going to calculate the net input. U, it's just the sum of the weights times the inputs. Just like normal. So we're doing this, we multiply, add it all up, we get a net input. And then what's the activation function? It's like this. So U is the input, F of U is the output, and so it's 0 over here. And then it slopes up with a slope of 1. So it's like a linear neuron, right? But it's not linear because it doesn't keep going down, so it's kind of thresholded down here. And then it chops it off here and it stays at max. So it saturates at U max, so if U comes in as like 9, then 9 goes out and that's as big as it can get. All right, so we got our pattern, we got our input, so let's do this. I'm going to leave that picture over there, so let me give you a minute to copy this down. We good? Let me check the Zoom. So you guys, this is over here so you can look at it. You got this written down. Oh, I need to tell you what we're going to use for our exam. Gee. So Umax is 2 here. Ready? So I'm going to rewrite the input vector across the top because that's what we're going to process. And you can even think, the best way is to think of this as running in time, again, because it's a recurrent net, because we have those recurrent connections. So time t equals 0, the x is equal to the input vector, and we're just going to list that up here. 0, 8, 1, 8. You know how you can tell somebody who has an artistic talent versus somebody that doesn't? Like if I started writing my name over here, start spacing it out. And then I would run out of room and squeeze it in over here, right? Our artists can look at that visual space and space it out and just do it. Whereas I always run off of that room. I thought of that because I ran out of room here. Okay, so then we're going to update. So what we're going to do is calculate at the next time step. We calculate the net input vector and then the new x value. So let's make our things to do that. So I want to start with the center one. It's like, let me space this a little better so that it looks like the center one. 5 over here, 5A, 1.0 here. I guess we're good over here. All right, so this is the center one. We're just going to do this as an example. So calculate the net input for this, which means you're going to take 1 times 0.6 plus 0.8 times 0.6 plus 0.8 times 0.6, right? So far. And then negative 0.4 times 0.5 and negative 0.4 times 0.5. So you guys do that. Write that out on your page. It's 5:06. It's been raining all day. You guys are tired and sleepy, right? So maybe this will wake you up, or maybe it'll just be that. If you had to do it to save your life, you could do this in your head, right? No. So you guys got this? 0.6 times the middle three numbers, and then minus 0.4 times the outside. Anybody got a U value?
98.
You got what?
198. Oh, wait, I was wrong. No, not that. That was like, I'm sorry. 1.16.
1 point what?
16.
1.16. I hear a 1.16. I hear another number, 1.16. Like an auction, right? 1.16.
90.
You guys validate that? Calculate this like our life depends on it. Even though it is. Anybody here do their taxes by hand? I used to a long time ago. I mean, this is a long time ago before there was software to do it. Find all the little numbers in the boxes and check all the boxes and add them all up and figure out your tax from the tables. Now you just turn the tax. So if you do something like that, yeah. Okay, 1.16, we're good. So what's the output? The activation function says linear slope. Is this less than 0? No. Is it greater than 2?
No.
No, so we just get out that value. Okay, so you guys see how this works. If we do this one here, we have to decide, well, what's over here to the left? We could potentially wrap around to the other side if we decided that was the topology of what the neighborhood looked like, which would mean that then these all lived on a cul-de-sac, right? But we're going to do this as if this is the end of the world here, the end of the earth here and here. So we take this one and times 0.6, and this one times 0.6, and this one times minus 0.4, and that's it. There are no clusters over here or that. So we get minus 0.02 here, 0.38 here, 1.06 here, 1.06. And this didn't have to be symmetrical, I just did it that way because it's following an example he had in the book. And so when it's negative, then we get 0 because it's thresholded. These all stay the same. And you can see what happened is the biggest one got bigger and some of the smaller ones got smaller. The three middle ones were big, and so they competed to make themselves bigger and knock down the other ones. And we'll do this one more time step. So T equals 2. Value minus 1.6. Apply the activation function. And you can keep doing this, and the big ones get bigger and the small ones get smaller. So maybe that's kind of like a bunch of fish in a fish tank. The bigger ones get more food because they swim faster and eat food, and the little ones don't get as much food. Or maybe more appropriately, like a pack of dogs. The alpha dog gets more food than the rest and gets stronger. That's the competition. I mean, there's things in life that are competitive and some that are not, and we take advantage of some of that. All right, so that's the Mexican hat network. Does anybody have a question about any of that? Anybody wondering why it's called the Mexican hat network? You don't, what? I mean, so if you plot this, so here's an 8, 2, 3, 4, 5, 6, 7, 8. If you plot it, I'm going to cheat and look at my values here. So here's 1. So the initial data looks like this. Let's get the middle one. Oh, 0 in here, right? There's what the initial data looks like. It looks like a mountain. Then after the next step, it looks like this. There. Looks like this. If you keep going, it starts to look more like this. Now you can see why it's called Mexican hat. It's like a sombrero. The person that created this said, I'm getting these things that look like Mexican hat sombreros, and so I'm going to call it that. You too, if you ever invent something and people start doing it, you can name it whatever you want. I highly recommend you don't name it something cutesy. This was reasonable because it looks like a Mexican hat. A lot of software languages tend to be created as just kind of a niche kind of a language. And then some of them catch on, and like Python and things like that become commonly used languages, and you look at them and there's all these weird names in there that came from either the cult movie that the developer liked or some weird Dungeons and Dragons reference, or all those names are stuck into the code. Like, for example, have you guys heard of Python programming language? Yeah? So why was it named Python? Sounds like a snake, right? Especially when you find out that the language version of it that most people use is called an Anaconda Python. Definitely a snake, right? And that is, this was named after Monty Python's movie. Those whoever first created it like Monty Python, and they were just goofing around, and who knows, maybe they did it as like their master's thesis project to create a different programming language, and they goofed around with some names. when you like to import a math, like a math library, and you end up importing NumPy. And I looked at that, I was like, what the hell, maybe NumPy? I don't know, or maybe it was a kid's book that the developer read, and there was a character called NumPy. So what I'm saying is, if you ever invent anything cool, don't name it something cutesy, name it something, I don't know, it makes sense. Or name it after yourself, like if you're gonna invent an airplane. Or you're gonna build Lear, you can name it the Lear jet. All right, we're done, I'm done talking.
5 minutes.
Yeah.